Public key cryptosystem, algorithm and categories. Asymmetric. Asymmetric cryptography, also known as the public key cryptography, uses public and private keys to encrypt the data. The keys are simply large numbers that have been paired together but are not identical. That's the whole meaning of the word asymmetric. One key in the pair can be shared with everyone, aka the public key, and the other key is kept private, aka the private key. Either of the keys can be used to encrypt a message. Right? The opposite key, which could be the private or public key, is used to decrypt the message, as you can see in the picture. Either one can be used to encrypt or decrypt. Symmetric. Symmetric key cryptography, also known as symmetric encryption, is a type of encryption scheme in which the same key is used both to encrypt and decrypt messages. There is no public or private key in this one. Such a method of encoding information has been largely used in the past decades to facilitate secret communication between governments and militaries. A kind of good example of it is the keys it is used for nukes and things. You probably see it in movies. Nowadays, symmetric key algorithms are widely applied in various types of computer systems to enhance data security. The comparison of the lengths and strength of asymmetric and symmetric. First of all, the key length is the number of bits in a key used by the cryptographic algorithm. Right? Asymmetric keys are usually much longer, example 1024 or 2048 bits, rather than symmetric key lengths, which are 128 and 256 bits. A digital signature. A digital signature is a mathematical technique used to validate the authenticity and integrity of a message, software, or digital document. In many countries, including the United States, digital signatures are considered legally binding in the same way as traditional document signatures. Basically, is a signature in an electric form. As you can see in the diagram, the sender has its original digital signature, which can be encrypted in the private key using an algorithm, right? And the recipient must have the public key with the same algorithm, right, to unlock the message through the digital signature. Right? The public key encryption using digital signatures and hash digests. Right? The hash function is a mathematical algorithm that produces fixed length number called message or hash digest. Right? The hash digest of a message is sent to recipient along with message to verify integrity. Right? The hash digest and message is encrypted with the recipient's public key, and the entire ciphertext then encrypted with the sender's private key, creating digital signature. Right? This is used for non-repetition and authenticity. Right? This basically is when they say the message is digest, right? That is the public key is at work. Right? But when the entire text is ciphered, right, the whole document or whole message is encrypted by the private key using a digital signature. The MD5 Hash Generator. The MD5 hash is created by taking a string of any length and encoding it into 128-bit fingerprint. This is basically a bunch of numbers and letters when it's encoded, usually long. Right? The purpose of the MD5 hash generator is to hide important data such as credit card numbers, passwords, bills, account numbers, etc., etc. Right? The MD5 hash are also used to ensure the integrity of files. Because the MD5 hash algorithm always produces the same output for the same given input, that means whatever message is encoded through the private key must be equal and the same in the public keys end. Right? So the algorithm must always be the same. Right? Users can compare a hash of source file with a newly created hash of destination file to check that it's intact and unmodified. Right? This is a example of the MD5 hash generator. Right? The sentence, this is an example, is translated into the MD5 hash, and this is then encrypted into a private key, and the public key user has to use the public key to match the MD5 to be able to read the message. Right, sending a message with a digital signature. First, I need to verify a digital signature. Right, the process of digital signature verification is purpose to ascertain if a given message has been signed by the private key that corresponds with the public key. Right? As you can see in the diagram, the signed message which is used on a private key is hashed, right? And then the hash value is then compared to the public key digital signature, right? And it must be the same as the original, right? That's why they compare it in the end, and if it is the same, it is verified and the digital signatures are the same. Right? 3 steps. The first step is to calculate the current hash value. Right? The hash value is a signed message and is calculated using a decryptor. For this calculation, the same hashing algorithm is used and was used during the signing process. Right? The obtained hash value is called a current hash value because it is calculated from the current state of the message. That means when you send it, it is then calculated into the different numbers or bits, or whatever you want to call it. And the person with the public key is then he can now use it to calculate the algorithm does all the calculating, but the user with the public key activates the hashing algorithm. Right? The second step is to calculate the original hash value. In the second step of the digital signature verification process, the digital signature is decrypted with the same encryption algorithm that was used during the sign-in process. This is the original part of the message or the information they're trying to send. The decryption is done by the public key that corresponds to the private key used during the signing of a message. Right? This basically means the public key must match the private key and the original hash value must match the current hash value in order for it to work. Right? We obtain the original hash value that was calculated from the original message during the first step of the signing process. Right? The third step is to compare the current and original hash values. Right? This is what I just explained, the two values, and then check the original hash value is obtained from the second step and the current hash value is taken from the first step. If the two values are identical, the verification is successful. Right? That means the message has been signed with a private key that corresponds with the public key. Right? If two values are different, obviously that means the digital signature is invalid and the verification is unsuccessful and you wouldn't be able to read the message. So basically in these 3 steps, right, you must be able, the both keys of the hash value must be the same in order to read the message. Right, there are some reasons for the invalid digital signatures. Right, if the digital signature is not real and is decrypted with the public key, the obtained original value will not be the original hash value of the original message, but some value. Basically, if you tampered with the original message, right, the hash values, when you try to decode it, it will be different from current the current message, right, the current hash value, because it's kind of self, you'll understand it when you see that. Let's say the hash value is hashtag 38B in the private, but somebody alters it and it doesn't come out as hashtag, it comes out as a $sign instead. It will automatically be invalid, right? If the message itself was changed, right, after it's signing, it will also be calculated different, right? Because if the hash value is tampered, right, the original hash value is tampered with the message, right, the two messages correspond to have different hash values, and you'll end up with a different message. If the public key does not correspond to the private key used for signing, the original hash value obtained by the crypto signature with an incorrect key will not be the correct one. This is just as the first one. If the public key doesn't be the same as the private key, right, the hash value for the private key will be different from the hash value for the public key, and it will not be able to decrypt.